Okay, now we want to talk about vertical motion. So far we've only been talking about things that are moving sideways. And then we had these three equations which could be used in order to predict how fast it would be going and how far it would travel. So now we want to derive some equations that will explain falling objects. And so in order to do that, let's watch this little, or snippets of this video on free fall. So go to YouTube and we can watch this.
Hello. We're going to do a quick little experiment here, analyzing the free fall motion of a ball that's thrown up into the air. We're going to collect video of the motion and then analyze the video using a computer program, see what sort of information we can glean from the experiment. So to begin with, I need to use this 1 meter stick to hold it up in the field of view so we know what 1 meter stick is. We'll need that when we analyze the video. And I have a rubber ball which I can throw up in the air, so I'm going to do that right now. We'll collect the motion of the ball on video, analyze it a little bit later. Here's the motion.
Now it's time to collect data for the video that we just collected. So I've imported the movie into my video analysis program, and I'm going to begin by first calibrating to indicate what 1 meter is on this little video screen. So what I'm going to do is fast forward the video to a frame where the meter stick shows up, which is right about here. And then I'm going to grab this tool and I'm going to say from this point at the top of the meter stick down to this point at the bottom of the meter stick is 1 meter. And this has got to be perfect or it's going to have effect upon all my data. So I think I did a pretty good job there. And now what I'm going to do is I'm going to indicate the origin point. And so what I'm going to do is fast forward the video to the point where the ball just leaves the hand. And that looks like it's going to be right about there. And I'm going to call that the origin location, the point where x is 0 and y is 0. And now what I'm going to begin to do is click on my ball. I'm going to choose the middle of the ball in each frame, and I'm going to click on it. I'm going to do as good a job as I can. I'm not really worrying about the X middle, the horizontal middle of the ball. I'm mainly worried about the vertical middle of the ball. It looks like I've hit the peak and the ball is moving back down. I want to be as accurate as I can. Being sort of missing the middle by just a little bit is going to introduce error into my results. Now I'm noticing the ball's going faster right now, and there's a little bit of
Okay,
motion blur.
so let me stop the video there because it is a 12-minute video. I encourage you to watch the rest of it. But what's amazing about this is by using some computer programs and a video camera, you can actually watch this ball rise and then fall and then analyze its motion. So what you should have noticed was that the ball started out down here and it traveled a certain distance, let's say in one frame. So I don't know how many seconds it was per frame on that, but let's just say for the sake of argument it was 1 second. So 1 second per frame, so that at the end of 1 second the ball was here. At the end of 2 seconds the ball was here. And then at the end of 3 seconds the ball was here. So what are you noticing? So you notice that the distance from here to here is larger than the distance from here to here, and then that distance is larger than this distance here. So notice that if this is the same amount of time, so this is going to be 1 second, and then this is 1 second, and then this is 1 second, but if it covers smaller distances each time, that must mean it's a smaller speed. So this is going to have a certain speed v going from here to here, a certain average speed going from here to here. But we could symbolize going from here to here a smaller v because it's going slower. And then this would be an even smaller v up there. So if it's not able to cover the same amount of distance, it must either be speeding up or slowing down. Since the distances are getting smaller, the speeds are getting smaller. And so when it's at the top of its trajectory, wherever it was, so up here, the speed is going to be 0. It comes to a stop. And then you notice that it basically was repeating itself on the way down. The distances were getting larger as it was falling, so it was speeding up. Well, what causes something to speed up? An acceleration. So that ball must have been accelerated. And the acceleration, you can even figure out what was the direction of the acceleration. It was down. So you notice that when the ball was falling, it sped up because the velocity was in the same direction as the acceleration. And when it was going up, the two of them were in opposite directions, so that the speed slowed down, it came to a stop, it reversed, and then it went back down. So do you remember the moving man? So in the moving man, he was initially going this way, came to a stop, and then started going back in the opposite direction. So therefore, there must be some kind of an acceleration that is acting on that ball. And we're going to call that the acceleration due to gravity. And it's got its own special letter, which is going to be the letter G. So G stands for the acceleration due to gravity, and it has its own special number, which is going to be 9.81, and then it's going to be meters per second squared, because it's an acceleration. And then notice that I went ahead and put the negative sign on it because gravity pulls down. So this is the acceleration caused by gravity. Now later we will talk about what is gravity and how does it do it. But for right now, we're just going to say that gravity pulls down on everything, and on the surface of the Earth, it causes this particular acceleration. Now, it depends on what planet that you're on, because different planets have different amounts of gravity. So that if you went to the moon has an acceleration due to gravity of around 2 meters per second squared. If you go to Jupiter, it has a much larger acceleration due to gravity because Jupiter is a much bigger planet. So it's going to depend on what planet that you're on. But guess what? We're going to be on Earth. So we don't need to worry about this stuff, and we're just going to assume that the acceleration due to gravity is negative 9.81. And it changes so that the higher up you go in the air, gravity gets weaker. So this number does actually change. But for all intents and purposes, here on the surface of the Earth, we're going to assume it does not change, and it's going to be a constant. Later, when we talk about gravity, we'll show you that G does change the higher up you go. So keep this in mind. G is going to be equal to negative 9.81. Now, for the most part, I'm going to use just regular 9.8. In your textbook by Paul Hewitt, he likes to use 10. So he rounds this to 10 meters per second squared just because it's so much easier to do math problems with a 10. But when you do stuff for me on your homework and on your labs and on the tests, use the 9.8 because that's going to be good to 2 significant figures if you'll do that. Okay, let's take a break, and when we come back we will talk about the formulas to use when you're going up and down.